In 1929, Edwin Hubble discovered the universe was expanding. For nearly a century, that was the answer. In the last 10 years, it has become the question. Two completely independent methods for measuring how fast the universe expands keep producing different numbers. Not slightly different. Stubbornly, persistently, embarrassingly different. Every attempt to find the mistake has failed. In April 2026, an international collaboration of dozens of astronomers produced the most precise direct measurement of cosmic expansion in history. They achieved under 1% uncertainty. They built an entirely new framework, combining decades of independent data. The gap did not close. It confirmed. This is not a minor calibration problem waiting for a better telescope. This is a crack running through the foundation of our best model of the universe. And the more precisely we measure, the wider it gets. To understand what is broken, you first need to understand what is being measured. In 1929, Edwin Hubble noticed something that should not have been possible. The galaxies he was observing were not standing still. They were moving away from us. All of them. And the further away a galaxy was, the faster it was receding. This was the first evidence that the universe itself is expanding. Not galaxies flying outward through static space, but the fabric of space stretching in every direction simultaneously. The rate of that expansion is called the Hubble constant. It tells us how fast space is growing, expressed as kilometers per second for every 3.26 million light-years of distance. For every one of those units you look outward, the universe is expanding roughly 70 kilometers per second faster. That number matters enormously. Get it right and you can calculate the age of the universe, the history of its expansion, the fate of its future. Every major claim in modern cosmology, the Big Bang, inflation, dark energy, dark matter, is built on top of it. Get it wrong, and the entire structure is wrong with it. So cosmologists have spent decades measuring it with increasing precision, using increasingly powerful instruments from increasingly independent angles. They expected the measurements to converge. They have not. There are two completely different ways to measure how fast the universe is expanding. They are independent in every sense, different instruments, different physics, different assumptions. In theory, they should produce the same number. They do not. The first method is called the distance ladder. Astronomers cannot stretch a tape measure across billions of light years, so they build a chain of calibrated steps, each one reaching further than the last. The first rung is Cepheid variable stars, stars that pulse with a regular rhythm. The speed of that rhythm tells you the star's true brightness. The true brightness, compared to how dim it appears, tells you how far away it is. Precise, reliable, used for a century. The second rung is Type 1a supernovae, exploding stars that always detonate at the same peak brightness. Once calibrated against nearby Cepheids, they become measuring sticks you can use across billions of light years. Combine these rungs, observe enough galaxies, and you get a measurement of today's expansion rate. The answer? Approximately 73 kilometers per second per megaparsec. The second method starts not from nearby stars, but from the edge of the observable universe. In the first 380,000 years after the Big Bang, the universe was a hot plasma, too dense for light to travel freely. When it finally cooled enough, light flooded outward and has been traveling ever since. We can detect that ancient light today as the cosmic microwave background, a faint, cold afterglow of the Big Bang that fills the entire sky. The patterns in that afterglow are extraordinarily precise. They encode the composition of the young universe, the geometry of space-time, the density of matter. Feed those patterns into our best cosmological model, and you can calculate, not just guess, but calculate, what the expansion rate should be today. The answer, approximately 67 kilometers per second per megaparsec. 67 versus 73. The difference seems small, a few percent, but these measurements now have uncertainties well below 1%. The gap between the two answers is nearly 5 standard deviations. In physics, 3 standard deviations is enough to claim a discovery. 5 is enough to know something is genuinely wrong. The first assumption was that someone had made a mistake. For decades, astronomers hunted for the error. They examined every rung of the distance ladder for hidden bias. They recalibrated the Cepheid measurements. They checked the supernovae. They questioned whether the cosmic microwave background had been analyzed correctly. No mistake was found. In December 2025, a team at the University of Tokyo measured the Hubble constant using a method that bypasses the distance ladder entirely. Their technique is called time delay cosmography. Massive galaxies bend light through gravitational lensing, creating multiple images of the same distant object. When that object's brightness changes, the change arrives in each image at a slightly different time. Those time delays act as cosmic rulers, an independent way to calculate distance, and from distance, expansion rate. Their result matched the local universe measurements, not the early universe prediction. This is significant. Their method shares no systematic errors with the distance ladder. If the discrepancy were caused by a flaw in how Cepheids are measured or how supernovae are calibrated, it would not appear here. It does. Then, in April 2026, the H0 Distance Network, an international collaboration emerging from a dedicated workshop in Bern, published what may be the most precisely constrained direct measurement of the Hubble constant ever produced. They combined decades of independent distance measurements into a single transparent framework. Dozens of astronomers, data from observatories across multiple continents and from space. Their result, 73.5 kilometers per second per megaparsec. Uncertainty, less than 1%. Their conclusion, stated plainly, this work effectively rules out explanations of the Hubble tension that rely on a single overlooked error in local distance measurements. If the tension is real, as the growing body of evidence suggests, it may point to new physics beyond the standard cosmological model. Meanwhile, the dark energy spectroscopic instrument mapped the motion of 15 million galaxies and found hints that dark energy may not be constant. Its density appears to be changing over time. That was supposed to ease the tension. It made it worse. There are explanations. None of them are satisfying. The first is that there is still a measurement error no one has found. This remains possible. Systematic biases can be subtle and persistent, but with multiple independent methods now converging on 73, and with the distance network's new framework specifically designed to expose hidden errors, the window for this explanation is narrowing toward closed. The second is early dark energy. Some theorists propose that in the first moments of the universe, an unknown form of energy briefly accelerated expansion before decaying away, leaving the young universe slightly different from what our current models assume. If true, the early universe measurement of 67 would be miscalibrated. The true value would be higher. Early dark energy models are mathematically viable. They are also not confirmed, and some data suggests they create new problems while trying to solve this one. The third is primordial magnetic fields. A study published in February 2026 explored whether extremely weak magnetic fields left over from the earliest moments after the Big Bang could alter the way hydrogen formed during recombination, the period we use to calibrate the cosmic microwave background. The mathematics is credible at specific field strengths. It requires fine-tuning that raises its own questions. The fourth is a cosmic void. In July 2025, researchers propose that our galaxy sits inside a vast, underdense region, a billion light-year bubble where matter is more sparse than average. In such a region, local expansion would naturally appear faster than the global rate. The tension would dissolve, not because our model is wrong, but because we happen to live in an unusual corner of the universe. The evidence for the void is suggestive. It is not conclusive. The fifth explanation is the one no one wants. The standard model of cosmology is missing something fundamental, an unknown ingredient, a physics we have not yet discovered, something that changes how the universe expanded at some point in its history in a way that makes the early and late measurements irreconcilable. If that is the answer, everything built on the current model needs revision. The universe has been measured more precisely than at any point in human history. The disagreement has not narrowed. It has hardened. Every independent method that was supposed to resolve the tension has instead confirmed it. The most precise, direct measurement ever published, released weeks ago, does not close the gap. It draws a cleaner line through the middle of it. Both measurements are right. Both methods are sound. The numbers are different. One of three things is true. There is a mistake no one has found. The universe we happen to inhabit is unusual in a way that distorts our measurements. Or the physics underlying our entire cosmological model is incomplete in a way we have not yet understood. The dream of every physicist, as one researcher put it, is to find something wrong in our understanding, so we can discover something new and profound. The dream is here. We do not yet know what it means.